Good morning. I think I'm going to start because I have too many slides. And then, my name is Anil Nori. I'm an architect, distinguished engineer in Microsoft. My profile is online, but I'm a data guy, been in doing databases for a long time. I pretty much worked on every relational database system company. And then for last 7 years, I've been building applications, especially mostly first-party apps, building commerce applications within Microsoft. Pretty much all our $100 billion revenue goes through our systems. And so this talk is about the journey that we did last 7 years, how we modernized our legacy systems into Azure, sort of cloud-based, systems. That's what I'm sharing today. My slides may look a little dense, but I have a tendency to put more stuff because when you get the slides, you have more content. But I'm not going to read, every line in that. But you will have the content, on the slides. And I'll just hold the questions till the end. And if necessary, I can always stay back, and then I can answer questions also. So let's get started. So in this session, I will introduce what the Universal Store Team is just quickly, and then just go through our modernization journey, and then talk a little bit about, as we modernized it, bunch of services, what are the typical storage characteristics of these modern services? And then figure out, what is a good fit, and then why Cosmos DB is a good fit, and talk about Cosmos DB use cases. I picked like 4 scenarios that we will cover, variety of different types of services, and then see how we have used Cosmos DB. And then also we'll show, how well is it performing, so I will go through that. And if I have time, I have one slide which actually is quite interesting to explain to people. Why does Cosmos DB work? How does it work? So it'll be interesting, but I don't know, I'll have time. And then end with a little bit of guidance on the storage itself, the storage guidance. So Universal Store Team is the Microsoft Commerce encompassing everything that we sell, also like our third-party stores that we sell, so third-party products, both for consumer as well as commercial. Anything you do on Xbox, so whether you're playing a game and then you buy some ammunition, within the game, or whether you're doing Windows Store, whether you're doing Office 365, anything that you purchase, or you go to brick and mortar stores like in Bellevue Square. So if you go and then buy it in the Microsoft Store, all of that stuff goes through, our systems, as well as, anything that our sales guys do it and our partners do it. For example, GoDaddy sells a lot of Office 365. So our partner channels also actually go through our systems. Everything from digital, physical, subscriptions, transactions. Every time you use actually any Microsoft product, like you launch actual Office, all the license checking and entitlement checking is happening in real time against our systems. So it's pretty mission critical. It cannot stop. And the scale is very high. And that's what I'm going to cover. So it sort of shows at a high level. If you look at the bottom, these are all the components of a commerce system. There's nothing unique about these things. It's just the way that we built it is different. But you have like an account management, catalog, pricing, purchase, billing, quotes, entitlements, all of those things. And then next it shows actually who are all the internal partners that are using our systems. So everything from Windows Store, Office365.com, Dynamics, Xbox games, Surface, Xbox One, Azure, DocuSign, all of those external guys also. And then the next layer shows actually what are the storefronts that you have. You can go to Microsoft.com, that's store.microsoft.com, or you can go to Xbox.com, our brick and mortar stores. So that shows actually what are the storefronts that you can go to. And then it shows different channels that is, you can actually have self-serve, most often that you can go and then purchase it yourself, or it's led by our sales guys, or are led by partner guys. And then the top, it shows actually what are all the, both consumer, SMB, enterprise, government, and then education. It's extremely, customer-centric, personalized, So, and then experiences are like, we want to keep the same experience, whatever storefront that you come through. And we are active in, huge number of markets. That means we support almost all the currencies that required in those markets. And then also a lot of restrictions on, you can buy certain product in certain areas and you cannot buy it. There are a lot of restrictions that come with the services. We support those. So there's almost like close to 1,000 microservices that we have built, and hundreds of terabytes of data flows every day, and millions of daily transactions that happen. And in fact, days like Black Friday and then Christmas Day, that Xbox is pretty heavy, the peak loads. So that's sort of really what the requirement, what we are trying to do, our group. And this talks about like, what are the things that we need, the key characteristics of the modern services itself. One, for us, it's extreme scale, and it must always be available. Certain things always means it's 100%. So like I cannot stop taking your payment, so it has to be 100%, so. And we built it as microservices, so exposing them as REST APIs so that other services can use it is important. And security and compliance, we come under a lot of, both financial compliance because we take money, like, everything from, SOX compliance, so we do that. And then global reach, again, available in every market. And then from a developer perspective, we need to make sure that as we build these services, we are agile, and then, we have real-time visibility for debugging purposes, what's happening, so real-time monitoring is key, because sometimes, you have something is getting, constrained, we need to really see, what APIs are really being, restricted, and then so we want really good insights. And, also we need to have feature agility, that we want to add things, much more rapidly. So let me start the journey from legacy to modern cloud services. So going back in time, like, maybe 7 to 8 years, maybe even 10 years, that because we have been doing commerce for a long time, like people who know MSN, it started actually as part of MSN. That's where we started, building commerce. So why modernize? So again, we built these systems almost a decade ago, and with too much legacy, these stacks were never really re-architected. So we built it a long time ago. We didn't really take time to do that. And there were too many silos, so every group, a billing guy said, I need to add this, we built a silo. So it became actually hard to enhance it also. And it was never designed for cloud scale in those days. And it was more or less scale up based rather than scale out. Scale out is more, the cloud scale is more or less 5-6 years, so that's what we started looking at before that. Typically, a very relational centric that, you put more beef, more hardware behind it, and then, scale up. Extremely SQL centric. It's not very surprising. A lot of us, we grew up on building on relational database systems, and then it's very relational model centric. And I'll go more later, so, and it's not so much really, as you really try to really build a cloud scale, some of the relational model actually constrain you. That's what our learnings, I'll share that. And lack of robust, HA and DR. And this is another thing that we never really designed it for predictability, predictable SLAs. Even if it is something low, I want to really know predictability, because only then, when I build an end-to-end service, I know that, okay, storage is going to take 10 milliseconds, computer is going to take this much, something else is going to take this much. So I can create end-to-end SLAs. If I don't know how much my data layer actually takes, how many milliseconds it takes, it's very hard to really build an end-to-end SLAs. And no COGS consideration at all when we built the systems. In those days, we owned the machines, we owned, the software, therefore everything was cheap. But now, it's on Azure, and then, so it's like every other, customer, that we need to really pay attention to what is the cost of really running, all these services becomes important. And the no service orientation, again, I'll go into this a little bit more later. No real-time visibility, and too many systems, and then too much duplicate infrastructure also. We actually at one point had 3 or 4 different billing systems, 3 or 4 different payment systems, because everybody built it, so, and then again, as part of this modernization, we tried to consolidate, lots of those things. So that's the reason why we modernized. Now, what are the storage issues? And mostly on-premises storage infrastructure. Again, it's not uncommon that most of us who came from big enterprises who go into the cloud, we started with building large-scale on-premise storage infrastructure. And when we started, a lot of these things started as single DB. It worked in those days because worked well when the transaction volumes are low. And we built it pretty client-server centric. What I mean by that is business logic was living inside the database as stored procs. So actually, I forgot to ask one thing, that how many people are very familiar with already, like I assume that a lot of SQL databases, and how many of you are already familiar with Cosmos DB? So yeah, because I'll try to keep it, because Andrew will come and then give a few more demos for those people who are not already familiar with Cosmos DB. But I think having the relational background helps to appreciate actually what we did. So, and I will go into a little bit more of some of the issues that we ran into being too relational centric. And no separation of compute and storage. Again, as we built the logic in stored procs, if I need to scale out, really I needed to scale out into multiple instances of SQL. That's the only way that I could scale out. And it gets very expensive to do that. And too much locking and serializability. So like people didn't take enough attention to really support like fine-grained isolation, because if you have large throughput, you will do that. In those days, our volumes were not low, not very high. Therefore, people took actually big locks. In some cases, we found people took like table locks and database locks, and then it worked fine. But as the throughput increased, that becomes a bottleneck. So we needed to go and then fix those things. And by default, everybody assumes that everything is required to be at strict consistency. Again, this is a learning that real world doesn't really work on strong consistency. There is always inherent delay and staleness, in business processes. And by really requiring, strict consistency, it limits your availability. Again, we'll see that. As we really evolved the volumes, we needed to put multiple databases, multiple instances. Then quickly, I needed to put distributed transactions. At one point, we were running 32-way distributed transactions. There's no way that can really work reliably. Something will fail, and then the transaction will abort. So, and then, as I said, scale up instead of scale out. Too many HA and DR mechanisms. We pretty much use everything that SQL offered. We did SQL mirroring, we did replication, log shipping, all of them always on. So every possible mechanism. As we evolved, every version of SQL Server, we adopted those things. Over time, we were managing almost everything. So, and expensive infrastructure. So because to run these things, we were running on SANs, and then in some places we had the Fusion IO cards, and then SSDs, and So, and another big thing is that we design the databases in a way that it is used for heavy OLTP as well as for rich querying, DW. Because the schemas were designed in a fashion that we were doing both on the same system, which, like, if you beat the system for both reads and writes, neither of them are going to perform optimally. So this is another learning that separating those things is very important. So if you look at some data model issues, one of the things that we learned is over normalization hurts. So why does it hurt? Because we normally normalize because we think about queries. When we build the data model, we think that, okay, I'm going to run these queries. Therefore, I will build these tables, and then I'll do joins. But think of really on the IO side, like when you do a write. Take a typical purchase order. The purchase order has order lines. I need to give billing address. I need to give shipping address. I want the payment information. And each of these things are normalized thing, it becomes a separate table. All I'm doing is writing a single order, which becomes like almost like 10 table updates. And that is going to hurt because my IO costs, my write IO ops are going to go up. And not only that, when you do reads, you are doing like actually sometimes 6 or 7-way joins to really build all of these things back. So the whole normalization was hurting us. So in fact, when we went to Cosmos DB, we denormalized it, and we've seen significant performance and cost benefits actually. And then other thing is referential integrity. So the referential integrity works well when you're in a single database. As I really tease them apart, for example, when we started, the same database was holding my orders, my billing, my payments. So I could actually keep referential integrity saying that, oh, actually order reference to this payment instrument, and then order actually payment. Billing also refers to this. Billing actually refers to this order. We kept all of these referential integrity across these multiple tables. As soon as we really build microservices, I said I have this order service, I have billing service, and payment service. We separated out the database, referential integrity breaks. So building referential integrity depending on that is hard. And not only that, if you really want to preserve it, and then it becomes sort of running distributed transactions across multiple databases and multiple services. So again, we spend some time, and then we still need some constraints, but there are some techniques that we use that actually mitigated those things. Plus, we could actually capture some of those things in the middle tier logic, so some of this constraint management. And strict consistency, like some isolation level, makes it cross-geo region high availability hard. If you require everything to be strong and strict consistency, and if I really need to replicate it across geos, then you actually have to wait till everything commits everywhere. That means your latencies you'll suffer like in latencies. And in fact, if a region goes down, you cannot even really commit the transaction because you really require that to be committed everywhere. So it poses availability problems. So we needed to really relax what the consistency requirements there. And finally, we learned that one size does not fit all. You cannot have same database for reads, writes, for real time, for online, for batch processing, for DW, and then so we actually separated them out for saying that the purpose of this is if it's transactional, then use it certain fashion, certain schemas. And if it is for a heavy query, then you have a different kind of data model. And because if you did one thing, one way that you build it for every possible scenario, then your SLAs will hurt. So that's again the learning that we had. So the modern service design principles we used we just went to microservices-based architecture. So it's pretty much like we have very fine-grained services, the unit of functionality and deployment. That's what we picked. So if the billing group built billing services, payment group built payment service, and then so every service that built, and then they have their own database, and then they have their own business logic, and pretty much like a separate microservice. And then I can independently deploy them and independently develop them, and I can independently operate it. And these are decoupled, but they actually execute the contracts and the interfaces are well defined, and therefore you need to support rich API contracts through REST APIs. And if you go with a scale-out based architecture, we had required strict predictable latency. That way, then I know that, especially when you have microservices and then each service is interacting with other service, I absolutely need to have strong SLAs between those services. And we chose actually, where possible, going with the eventual or weaker forms of consistency. There are certain cases that you absolutely cannot really go with weak consistency. You need a stronger consistency. But actually, a majority of our services run at eventual consistency. Again, eventual consistency does not mean that you're reading uncommitted data, or you are always reading committed data. In fact, in Cosmos DB, using certain forms of consistency, you can actually read your writes, because that's the other requirement that we said, hey, whatever I write, I should be able to read it. Otherwise, it's broken, the system. So again, consistency does not mean that you're reading something random. It's predictable that whatever you write, you can read it. But in some cases, you may read stale data. Suppose if I wrote something, when you read it, let's say I wrote the billing guys, the order actually is accepted, and then somebody is checking order status. If the order status that's fulfilled is like few seconds delayed, it does not matter. I will try it again, next time it says it's fulfilled. So those are the compromises that we have done, and we made sure that it's globally available, and then the rich semantics, we try to capture them in the business logic. So let's quickly go through certain real-time transaction characteristics. For us, a lot of the systems that we build which are real-time, like payments, ordering, billing, those things, these are typically API invoked. That means somebody is sitting in front of a in front of a UX, and then trying to really make a payment. It's invoked at that API, so the response has to be very quick. But most of the time it's object at a time operation. I'm not running fancy query, so I'm just inserting something, and then it's a key-based lookup. When I want to really look up something, I know my transaction or the payment or order ID or something using which that I can actually look up, and operates on small amount of data. If you look at my order itself, that order form, that whatever order capture, it's not huge. It's orders of kilobytes, not megabytes. But I do need extreme scale and predictable low latency. And generally the data is partitioned by user ID or transaction ID. For most of our workload, either it is partitioned by your MSA or your AAD ID or your transaction ID or a device ID. So which actually has good characteristics because the cardinality of these things is very high. Like we support a couple of billion accounts, and that means I can nicely partition it across a nice horizontally scaled out cluster. But I do need real-time cross data center consistency wise, in some cases strict, in often eventual, high availability. In some cases I need to active payment. I cannot stop. So therefore, I want to write it wherever I can write it. I need to capture my payment transaction. Eventually, I will merge and then resolve any conflicts. These are some example services for that. So that's sort of this thing. To contrast, I'm not going into details, but to contrast this kind of service with, let's say, we have a bunch of services that do batch and then backend services. Here, these are like periodically invoked. Let's say I'm doing a renewal of your subscription. It doesn't happen in real time. There's a background process that wakes up and then checks which are the subscriptions that have expired, and then it sends out email saying that, okay, you need to really renew your subscription. So there I need to really again look at sometimes key-based, sometimes maybe I want to run a query. But here the latency is variable. It depends on how many people actually subscriptions are expiring that day. It's varying load. So I don't expect the same latencies like the transactional service. Therefore, the storage characteristics, the storage systems that I use can be different for this one. Similarly, you have management and portal services. This is again, I'm managing like admins manage. They're adding a payment payment instrument, or like somebody is really doing support, or a partner portal, or those kinds of things. They do require API in real time, but their throughput requirements are not as heavy as the real-time transactional services. You normally don't do hundreds of thousands of transactions per second here. And the last one is really like a complex query analysis. So here is where I want to run rich query, and then analytics, machine learning. Here it's mostly set-based operations. I do searching, I do complex query, and it operates on huge volumes of data. And it can be like, because I want to run queries across my payments, my orders, my bills, my entitlements, I gather data from all these services into some common place, whether it's a SQL DW or whether it is Azure Data Lake. That is where actually I'm going to party and then query there. The trick is how quickly can you get your data from the real-time systems into these warehouses, so that I get almost like near real-time query capability, because we chose to really separate out transactional services primarily for write purposes. Mostly they're doing simple reads and write. You just saw that object at a time operations. Set-oriented operations is a different storage system. The key is like if I make a payment and then I go here, how quickly can I see it? And we built actually certain query services to do those kinds of things. So for these purposes, for the real time, we basically said, we will pick, globally distributed database service, which is Azure Cosmos DB, because we pretty much running on-premise SQL. As we migrated to the cloud, we chose Azure Cosmos DB. And going back to really the model slide, I said I want denormalized data model, and then I want eventual consistency. I want globally distributed. I want high availability. We looked at all of these characteristics. If you look at the characteristics that are laid down there, and we said, okay, Cosmos DB can meet. Can I do the same thing on SQL? Of course you can do that. But I'm actually it's underutilizing SQL in that case, because I'm not really doing any query. I'm not doing strict consistency. SQL doesn't give me today any delay, weaker forms of consistency. But you can do that if you live with strict consistency. But we found Cosmos DB to be, again, COGS is also a factor. So I do want to make sure that my costs are also, is at lower levels. So now the journey, the next few slides that I will go is really primarily focus on Cosmos DB. And I'm only going to focus on real-time transactional services. I'm not going to talk about all the other services. So let's look at Azure Cosmos DB fit itself. So this is globally, massively distributed, massively scaled. And it supports multiple models. But we picked actually mostly simple, object at a time, NoSQL kind of patterns that we picked. It's a key value store. That's how we use it. We don't even use it that much for indexing. Although in some places it can index it, auto-index it, but we found that most of our patterns are give me the primary key, I'll get the record back. So Cosmos DB fit, it's elastic scale. I can actually scale it dynamically, the size as well as throughput. Both of those things can be scaled. As my data increases, I don't want to worry about it, and then Cosmos DB can take care of that. Again, the throughput also. I specify my request units, and then it can actually scale out, and it automatically can elastically increase and decrease. And transparent partitioning. This is another thing that is important to us. Is that we don't want to deal with partitioning. In fact, on-premise SQL databases, we did a lot of external partitioning. We built a lot of partitioning logic to run on multiple SQL instances, and we were routing the requests to different SQL instances, and it becomes a little complicated to manage all of those things. With Cosmos DB, we said we'll take a dependency on Cosmos DB to really do all the transparent partitioning. And again, global distribution is important, which means that I need to run on multiple regions, both for the disaster recovery purposes, as well as sometimes my load comes from a different region. Let's say I have replicated in the eastern region and then the western region, and a request may come into eastern region, then I want to go to the closest one for the reads. And then if it comes to the west, I want to close to the closer one that is the western region. So both for the purposes of really serving the requests as well as for DR, we wanted global distribution. And as I mentioned that we wanted varying consistency levels. There are cases where I absolutely want strict consistency. There are many cases I can live with weaker forms of consistency. Therefore, we wanted a tunable consistency, which again Cosmos DB gave us, and then we use that. And I mentioned high availability. There are other nice features that we use. There's one thing that we use. I explicitly called out time to live counters on documents. Is for a lot of privacy and then for the compliance purposes, we can only keep data for a certain time. So those, again, managing them actually is hard. Therefore, we actually set the counters in Cosmos DB. Then after a certain duration, those documents go away. So for the compliance, for regulatory purposes, that we actually leverage some of the features that Cosmos DB gives. And then it supports multiple API models, but we don't really use it. Actually, although we use Azure Tables APIs because we have been using Azure Tables, now we are using Cosmos DB. So let's look at predictable SLAs. We primarily write as JSON document, flexible schema. Primary key becomes the document ID, and it supports efficient indexing. Although we don't really we actually don't by default index everything. We pick actually what indexes that we want. In some cases, we just only have the document ID and no indexing. In those cases, actually, we can compress the data also, and that decreases the size of the document, and then you get better RU utilization actually. And predictable latency is very important for us. And Cosmos DB ensures less than 10 milliseconds up to at P99 work loads, both for reads and writes. Writes is something new now, but it can do for both. And predictable throughput. Through reserved provisioning, you can do that. This is another difference, is that until now, most of the systems, it's more or less based on storage costs or so consumption based, but Cosmos DB is reservation based. I know that I'm going to reserve saying that I need this much throughput. I'm going to run 100,000 transactions per second. That means I need 1 million request units. Please allocate that for me. So it ensures that you get that predictable throughput. But at the same time, whether I use it or not, I'm going to pay for it. So that's the thing that you need to manage it. You don't want to over provision, but there is a balance, and it does provide certain APIs to really adjust it dynamically, but you don't want to really keep doing that. So picking that right thing is important, and it guarantees availability 5 nines. So this is again at this Ignite. They have announced it. We were getting 4 nines already. So the scale is Cosmos DB. It basically it spans across the whole the scale out cluster, and what we need to worry about it is the logical partition. Take for example every order or every payment. The primary key for us is my user ID. All I really need to tell Cosmos DB is that user ID is the primary key. Cosmos DB internally maps those logical IDs to physical partitions. Because if you look at our user IDs, there's like a couple of billion user IDs, but it doesn't really create a couple of billion partitions. So it underneath it actually provisions physical partitions. But that is transparent to me. We don't really need to worry about that. But I actually put some calculations in the slide. You can read that. The way it actually calculates it is that so it takes actually what is the total run units that you have, total request units that you have, and total size of your document collection, and then it actually divides it by the physical partitions that they have internally, and then it calculates that. So if I have 1 terabyte my document collection, physically let's say they have 10 or 50 GB, then you're talking about like 1,000 or 200 partitions that physically they created. Again, that is variable. Cosmos DB itself started with sort of medium-sized partitions. Now they are increasing it. Over time, it will increase to bigger things, so I don't want to worry about it. Every time they increase the partition size, I benefit from that because my cost efficiencies will go up. So that's the scale. And from a throughput perspective, Andrew explained it. So at his session yesterday, the notion of really these request units. It's basically a combination of how much memory you use, how much CPU you use, how much IOPS you use. So the simple thing is, if you have a 1K document and then if you read it, then it's 1 request unit. If you do an insert, I think it's like about double that. If you do upsert, it is like you're doing a read and write. So you can actually calculate that. And then we look at our transactions, and then we say, my order document, if it's a 2K document, and then if I'm writing it, let's say 100 per second, then it's like 200 RUs per second. That's what so it's calculatable, and based on that, we actually set our RUs across the whole so our Cosmos DB document collection. So the things to keep in mind when you're really provisioning RUs are your document size. And what we found is that often we didn't really need indexing. Therefore, we actually could compress the payload. And we got sometimes 50% improvements by compressing the payload. Then, well, I'm saving 50% RUs. So that's a benefit that you do that. But if you do need truly indexing, then you cannot do that. So it depends on your workload. And then again, write cost is more than reads, and update is even more expensive. So we actually we very seldom we do updates. We do most writes, because like I'm not going to update my order. So if you change your order, it's actually change order is again a new order almost. And same thing like with the payment, if you pay something, I'm never going to change your payment transaction. You may pay more. It's just doing insert. Cosmos DB insert pretty much like an append, and it's incredibly fast actually. So we see latencies in some cases like 5 millisecond, 6 millisecond latency. And if you do a lot of index creation, then again the cost goes up. And again, consistency levels also matter. If you do strict consistency, strong consistency, it costs more than if you do something like a session consistency. If you can live with session consistency, that is good. I'll explain what that is. So I was going to really have Andrew come and then show you a few demos, but I've decided to combine. There are 2 demos. Instead of his coming twice, I will just defer that. In a few minutes that we'll go there. So let's talk about replication and high availability. Again, Cosmos DB does automatic replication for me worldwide. I can pick the regions, it goes and then actually replicates it. Today, most of the time, you have a write region and then you have a bunch of read regions. And when you read, you can also specify which are the preferred regions that you want to read it from. But moving forward with active-active, I can actually have multi-master regions. So I can actually have both 2 regions, I can write it. I have a slide that I'll go through that. Again, all regions are hidden behind one URI, so it can automatically pick that. And customers can actually dynamically add, regions, so add more and, so remove more. And we can support both automatic as well as, application control failovers. In some cases, we don't want to really, we want to really fail over at application level. We don't want a disaster to fail over. We actually can manage that failovers ourselves, so we do that sometimes. And let's look at active-active. But before that, let's look at consistency. This is an interesting thing that Cosmos DB did, is it supports multiple levels of consistency. Strong is, everybody knows what strong is. It's like people who are used to sort of a strict isolation, so in SQL, that sort of maps to strong. But strong consistency in distributed systems is hard. People who have, theoretically there is a theorem called CAP theorem, which you cannot get both availability and consistency both at the same time in distributed systems. Because inherently, like if you need strict consistency, what it means that writes needs to happen everywhere. If one system fails, then you cannot really commit it. That means you lose availability. But if you relax it and then you say, you know what, I actually can live with bounded staleness, which means that the writes actually happen in other regions slightly behind. I write it here, immediately it commits into the write region. All the other read regions get within certain time duration. That's the bound. Let's say I can set it to, let's say, 5 seconds. So within 5 seconds, it tries to really propagate to all the other regions. Well, what happens if I fail within the 5 seconds? Well, you could really it's not a data loss, but in other regions, that the update has not propagated yet. And eventually, when the site comes back up, Cosmos DB will propagate it. And also, within that 5 seconds, if you went and read from some other region, you may not see that immediately, that update. That is where your relaxed consistency, if you can tolerate that staleness of few seconds, then bounded staleness works. Session consistency says that if you want to read what you wrote, if you're willing to manage a token, which basically whenever you write to Cosmos DB returns back a token, a cookie, and then in the cookie it actually says that which region actually it wrote it. And then if you can carry your token, if your cookie, and then give it back to Cosmos DB, it tries to read it from the best place, whatever is close to you, and it compares the time, so basically it has kind of a timestamps and then says, I'm reading it from here, but the cookie says actually most recent one is written at the right region. It actually sends that request there and then gives you the most up-to-date data. So it manages it for you. However, your application needs to manage that cookie, which we found it not that difficult to do that. Because most of us have some middle tier logic, and then most people actually have a data access layer on top of the data storage itself. The data access layer, we built that, we actually manage that cookie, and then we propagate that. So pretty much 70–80% of our systems use session consistency. It works beautifully. And it is also half the price. I mean, in terms of the RUs, the strict consistency is more expensive than session consistency. And there are other forms of, even weaker forms of consistency. We use it in some cases. But I think that I'm a fan of really the session consistency. So I wanted to take a few minutes and then talk about the weaker forms of consistency. A lot of times people argue saying that you must have strong consistency. Especially I came from a relational background. People say that. But the thing is that most of the time it's an insert, and then writes are never lost, and eventually I can merge. So can you tolerate if you can tolerate a little bit of staleness, it's like one, I don't lose data, and it's eventually consistent. What's the problem? So, and if you look at other than strict financial things, like if you take supply chain systems or if you take ordering systems, most ordering systems means you're capturing the order. What happens after the order is it sends it to inventory systems and it sends it to actually supply chain system. It's not going to happen in real time. It is inherently a workflow-based system that happens. So inherently that staleness is built into the end-to-end business processes. So I don't need to really require those things. And data is published asynchronously. And one thing that to get this eventual consistency is we don't manage relationships across services. I don't want to do that. And the way we manage that, I talked about this referential integrity, is that we never change our primary keys. I'm not going to change your MSA or AAD ID. That's the primary key. The benefit of that is none of the foreign keys are going to break, because I'm never going to change your primary key. I may write multiple records, but I'm not going to change the primary key. So I don't need to strictly manage referential integrity anymore, because that our policy is that primary keys are immutable, and then so I don't need to really maintain. And we also don't delete data that much, because a lot of the data that we archive it and then we eventually purge it, but I'm not going to really perform that many deletes. So if I don't do deletes, if I don't do update, why do I need referential integrity? So that's how we solved, so in fact, that's a pattern that works well when you're really doing it across multiple services, microservices. It doesn't matter whether you use SQL or Cosmos DB or any system, it's a good practice. And it also sort of encourages to build more decoupled services. Here is an example of multi-master active-active. So take, for example, payment transaction. So payment transaction, I take a credit card charge. It must be always available. And mostly it's insert, I write it. So let's say when a payment transaction comes, it routes it to one of the Cosmos DBs. And suppose it is failed now because, let's say, that region failed. Then I don't want to really lose that right. Cosmos DB actually writes it to the other region. So I have 100% write availability. When the first region, that failed region, comes back up, Cosmos DB actually merges these things. It actually has conflict resolvers. But in our case, the conflict resolver is like the last writer wins. Because my payment transaction one went here, two went here. I need both of them, so it just merges. So we got beautifully like 100% availability. So let me actually hand it over to Andrew now. So he'll do like 10–15 minutes of showing the things that I talked about in Cosmos DB. Then I'll come back and actually cover some use cases. So maybe you have 10 minutes. I reduced it. Mike.
Okay.
Yeah.
Cool. So today we're going to demo a couple of things about Cosmos DB. And what I've done is I've set up a demo environment. I have 2 virtual machines deployed in very far geographic distances, one in West Europe and one in West US. This is where I've deployed my application to test active-active, as well as I have a Cosmos DB account for which I have deployed in each of these 2 different regions. Now, setting up active-active in Cosmos DB is very simple. What you do is at the time of account creation, you just select multi-region rights, enable it. And then from here, it's very easy. You go into the regional configuration, and you can add and remove regions by simply clicking on a map and selecting which regions you would like to use. For the time being, I have set up my account in West US 2 and West Europe to correspond with where my virtual machines are. And what we will demo is 3 key properties. One is I'm going to follow the 3 V's: volume, velocity, and variety. For volume, what I'm going to show you is elastic scale. By volume, I'm talking about lots of requests. Throughput, how do I handle lots and lots of requests dynamically and scale that up and down across a large cluster of machines? For velocity, I'm going to show you the benefits of a active-active deployment, the low latency that you can achieve. And then variety, we're going to actually show you just how easy it is to then build such systems and maintain productivity on these. So let's dive right in. I'm going to go into my first VM. This one is my virtual machine in West US 2. And what you see here is I have a simple application. What I do is I spawn a bunch of tasks called insert document. And within each one of these tasks, I do something very, very simple. I just, in a tight loop, I create records against Cosmos DB. Now, what this allows me to do is I'm going to just be blasting as many writes per second as I can against Cosmos DB, against the collection that I've already created. So first, I have a collection here right now with 50,000 RUs. And as you can see, 50,000 RUs is translating to about 5,000 writes per second. And if you amortize this to monthly requests, you'll have roughly about 100 billion monthly requests. Now, if I pause this for a second, and let's have this scenario where, let's say today I have 50,000 request units per second, but then I find that in my business, we're forecasting that we're going to have 10x growth. So how do I go and handle that in Cosmos DB? Well, I can simply go into the Data Explorer, go to the collection that I was writing to, and simply change the amount of RUs that I have provisioned. So let's scale this up 10x. And what you'll see is this will happen instantaneously. We'll automatically handle all of the partition management to scale this out. And if I run this workload again, what you'll see here is that we'll have much more throughput. In fact, what will happen here is you'll find that the VM will slowly become the bottleneck. Let's see what's going on. Let me hop back over. I have 500,000. There we go. OK, so now that I have this VM driving 150,000 RUs, how do I scale out my workload across multiple VMs? And maybe we can make this a little bit more interesting. What if we also have these writes coming in from multiple regions to really take advantage of our active-active topology? So let's jump over to our West Europe VM. You'll see that I'm running the exact same code with one slight modification. When I instantiate the Cosmos DB client, I add 2 things. Number 1 is I tell the client, hey, which region would I like to write to? And number 2 is I also want to instruct it that, hey, I would like to use multiple write locations. I acknowledge that. So if we go and run the exact same code here, where we're going to go ahead and blast a bunch of database writes, you see now that we're driving tens of thousands of writes in each one of these regions against my same Cosmos DB endpoint. Now, driving a bunch of writes to the database is interesting and all, and getting throughput. But there's another aspect to performance, and that is latency. So if I were to go to each of these VMs and also do a quick load test on latency, let's see. Let me go to this code. What I have here is just a while loop where I issue a request, and I have a simple stopwatch where I'm timing the latency of that request and then emitting it back out. So first you see that I get single-digit millisecond very predictably out of my West US 2 VM talking to my Cosmos DB in the local region. And as I move over into my West Europe VM, let's go over to exact same code. Whoops. So you see the latency right now is not so great, right? 300 millisecond latency. Well, why did this happen? Well, what you see here is I've actually set a manual configuration in terms of homing requests, and I can determine a failover priority on a per application basis. What I've done here is I've intentionally misconfigured my West EU VM to talk to Cosmos DB and West US 2, just to illustrate the importance of bringing data closer to where your users are. If I go and bring that data closer to where my users are, I replicate my data to West Europe, and then talk to the exact same instance, but to the local region. Now you can see that no matter what region I am around the globe, I can achieve very, very low latencies, single-digit millisecond latency on the exact same data set. Now, lastly, I want to show you one last kicker. If I have a highly partitioned database that is also highly replicated, one of the big challenges traditionally is how do I manage all of these partitions and how do I manage, let's say, my schema across all of these partitions. If I have a development team that, let's say, says, you know what, I just want to add a new property to my records, and I want to be able to query that. Well, doing an alter tables create index across many partitions, across many replicas, well, there's a bit of management there. Not only that, the business has told me I need high availability. There's no maintenance window. So how do I go ahead and make this a friction-free development experience? Well, the nice thing is Cosmos DB itself is a schema-agnostic database with automatic indexing. So let's say here I go into my database. I have a record here. In this case, I'm simulating a video game where I have a bunch of player records in my database. And then let's take a volunteer. Hey, do you play video games? No, sorry. Oh, does someone here play video games? You? Okay, let's add a property to our record. What's a good property you want to add to our player document? Okay, you want to put like a game ID on this? Or which game? So let's say our gamer is playing Halo. And now what I want to do is I have multiple different games for all of my players that they can go and switch between. But I maybe have, let's say, a single sign-on solution to track all of them across this. I quickly just go add a property to that record. I can now go over to a query and then simply do, hey, let's take a look at all of the records where I have a record whose game is Halo. And you'll see that with automatic indexing and a schema-agnostic database, I can also make this something that's very, very easy and welcoming to work with. Thank you very much.
Thank you. Do I need to switch this or?
Oh, yeah.
Okay. So let's go through, like Andrew, we take advantage of all the things that, so he demonstrated. I just wanted to get you a feel for, so how the Cosmos DB, all the things that I mentioned, latency, availability, active, just give you a glimpse of really the capabilities. I'm sure that there are labs that you can go and then, do more, more detailed dive-ins into these things, So we covered this, the demo. Now what I want to really, this pattern, because I previously mentioned saying that, hey, we want to really use Cosmos DB mostly for writes and then transactional, but I don't want to ignore query, so I still need to do my querying. So we actually use Cosmos DB change feed as a way to really push the data almost in near real time into the data lake. It could be DW or ADL or whatever it is, and then there the data actually we can query it. In fact, not only query it, we actually can build very quickly the tables in a fashion that Power BI also works on top of that. So so if you look at this, the left-hand side is the transactional system, and all of them, the Cosmos DBs, we use the Cosmos DB change feed and then push to ADL. An interesting thing that we built is the green box called query service, which not only pulls the data from the lake DW, there is some data that is still coming on the feed, and that is the most up-to-date data. I can actually query that also. We pull that. So it's like a union between the data that is in the feed as well as actually the data that is already fed into ADL. So that way then I have most up-to-date view of my data. I did a purchase. The purchase data is ingested into ADL as of like, let's say, 10 minutes ago or 20 minutes ago. But what about the purchase I just made? Well, that comes, I can query in real time, go and then query it from the Cosmos DB itself. So this way then, we quickly built the read-write separation without losing the query capability. So that's the pattern. Sometimes you hear the term like Lambda architecture. This is what that is that it just basically separating out the read-writes into different systems. So we talked about cost. These are some of the ways to really optimize your cost. Pick the partition key with high cardinality, because otherwise you get hard partitions. And in some cases, you do get really hard partitions because of your workload. What we do in those cases is that we have done some external partitioning ourselves. I have a case that I'll show it to you right now. And then again, we control where we build the indexing. We actually scale up as Cosmos DB plans to increase the underlying partition sizes, then the cost becomes more efficient also. And consistency model, choose session consistency. You can also read from secondaries. So let's look at some use cases. First one is Microsoft Rewards. I mean, I'm sure that a lot of people, you guys see, if you use Bing or if you use Xbox, so you use Windows, there are like suddenly the things pop up saying that you can play this quiz and then you can do. So these are all, you get rewards for that. And that's a loyalty program that it reaches customers to drive the engagement. So we want you to engage with our systems more. In return, there are some incentives so through that. But what that means is that I need to keep track of your engagement, your scores, how many times you played, how many incentives am I giving you. That's what our system takes care of that. Basically, it holds your profile and then your activities, your point summary. Over 30 million active users, and the hash is basically, we hash the user ID, and the document size varies from few kilobytes to sometimes 500K. And our workload today is that we run about 3.5K queries per second, and then 2K queries write. The database size itself is not that big. It's like about 250 GB, and we provision like about 100K sort of request units. So this shows actually two collections. The key things to really look at here are, so the bottom, so the leftmost, the top, this graph shows the requests, number of requests over a minute, so how, and then the bottom, the one on the bottom, the right side, it shows actually the RUs consumed. It's consuming about like, between average about 2K, so RUs that it consumes. And it's summarized actually higher up saying that the average throughput is about 14.84K RUs, and then average requests are about, it's about 3.5K queries per second. Similarly, the right-hand side, is very similar. It's a different collection. As for the latency is concerned, so if you look at the bottom three ones are showing like average like 5 to 10, millisecond latency. I just took this dump just last week, and one of the regions is, so we need to go debug it. I haven't done that yet, but I just said, okay, we need to go find out why that's, I think it is the west region is showing a little bit higher latency. We need to find out why. We haven't done that debugging yet, but all the others, but overall the average latency is quite low. So if you look at, the average load itself, if you took it overall, you get like about 10 millisecond latency here. I think once we debug, why that the west region is high, we can get it less than 10 millisecond latencies. The next one is, we have a service called Contact Permission Master, which is like a lot of these marketing events that we conduct, people give their email addresses, and give their phone numbers, they give their visiting cards, and then they'll say, okay, I want to hear about Azure events or Xbox events or Windows events. Then we'll actually contact you saying that, oh, there is this promotion happening or there is this event happening. So you get these emails. But they actually give preferences saying that, what you want to hear, what you don't want to hear. You can subscribe and unsubscribe. So before we actually send out emails, we actually go and then let's say Bing wants to really do a promotion, our office wants to do a promotion. They talk to us and then saying that for each of these email, like they give hundreds of thousands of these emails and then give us the preferences, what they want to receive and what they don't want to receive. So it's a bursty load, but when they give the batches, it's big load. So that's what the contact permissions, we pull the contact permissions, the preferences, and then we give it to whoever the client. The clients can be Skype, Xbox, account.microsoft.com, or Outlook, all of those things. We support over 100 partners, and so there's 7 collections. The largest one is about 12 terabyte size. Smaller documents, we partitioned into about 2,000 partitions, and then that's what we didn't do it. Cosmos DB does it transparently, and then it's spread over 2 regions, and we use session consistency. We tested it for 4,000 TPS. Actually, we run about 4K, but we tested it for 12K. It works fine, and we provisioned it about 500,000 RUs. If you look at again the graphs, that show that the key thing to really look at again are, the numbers are like, the interesting when the wavy one is the number of requests aggregated over 5 minutes, and then the bottom one that shows actually how the RUs are used. If you look at, we provisioned it for 200, for the 200K, but actually we are using only about 50K. We sort of over provisioned it. And this is the latency graph that you can see that on the right-hand side. 10 millisecond latency is what SLA says, but it's really a bit less than 2 millisecond latency we are getting. The real one, the actual one is we are getting about 2 millisecond latency. And the write latency is about 5 millisecond latency. And if the thing to see is it's pretty straight. It's like, it's not, we don't like waves. We don't like spikes. So we want really pretty much like even if it is like I need to set it high, the predictability is very important to us. And then you see that the graph actually gives me that. And then the last one that I want to show you is, this is a big one that we are just rolling it out, is the entitlement service, which is any time that you use any of Microsoft product, that the license checks and my entitlement checks happen here, whether it is licensing or purchase time, or whether it's Xbox 360 or Windows, or all of those things, they hit that. The primary use is to store the entitlements, which actually stores your ownership of that purchase. Extremely read heavy, because entitlements are written when you purchase it, but they are read all the time actually whenever you use it. And we designed it for like 5 nines. And we migrated this off discrete on-premise SQL to Cosmos DB. We have about 120 billion entitlements, and we actually migrated those from discrete SQL into Cosmos DB. And in some cases, actually, we put something on top of Cosmos DB because we do have certain partitions, certain regions which are heavily loaded. So instead of really, we couldn't really find a perfectly uniform key. So we had to do some manual partitioning ourselves, manual application-driven partitioning. So that's what, if you see this, we have 3 collections. Each collection is partitioned into 4 regions. For practical purposes, let's look at one collection. It's 4 regions. And we did that outside. So we created, in some sense, that I have 3 collections and 4-way partitioning and done in applications. From Cosmos DB perspective, it looks like almost like 12 collections. That's what we are dealing with. So take one example. So here is where I showed that the bottom picture. It shows that I have a collection 1 that is replicated on the eastern region 1, and then I have actually a central region collection 2, which is again replicated into south region, and then I have in Europe one collection, and then I have in Asia other collection. And this is what we partitioned it externally. So when a load comes to us based on the user ID, we have actually a lookup table, and then in the lookup table we'll tell you which specific region to send this to. We did that only to even out our own so the propagation of the requests, because the requests globally are not uniform. in sometimes US is much more heavily used than Europe. So we didn't want to build one humongous, really a Cosmos DB cluster and then let it deal with unevenness actually. So therefore, we did our research and then said these are 4 different ways to partition it. But each of these application partitions one, we use Cosmos DB. Overall, it actually about 70 terabytes of documents. We provision about 10 million request units, and it actually serves about 200,000 requests per second. It's very read heavy. And the way that we do lookup is we have something called a lookup service called global lookup service. That itself is built on Cosmos DB. Because we need to find out, given that Anil Nori at msn.com, we need to find out, is he homed actually in US or Europe or Asia or where? That lookup table is again, we do it using a global location service. And that's what this global location service is. I actually want to sort of end so that at least, this is actually an interesting slide, but it requires deeper dive down. So eventually, I think if you look at summary, that we use real-time transactional services, Azure Cosmos DB, some batch backend Cosmos DB, plus in some cases SQL DB. Management portal services, we use Cosmos DB. For query, we use ADL, SQL DB, SQL DW. So that's how we partitioned our services. The best practices for Cosmos DB: uniform partitioning, small documents, pick session consistency, and as Cosmos DB offers larger partitions, you get better efficiencies. Distribute your reads. Take advantage of the other regions. So we can set the preferred regions so that you benefit from reading it from other places. And key-based access, we can do simple list queries on that. And summary, we found it's very well-designed storage platform for us, and it's suitable for transactional services, high throughput, scale, low latency, predictability, and then tunable consistency. And the team is very responsive. So I can take a couple of questions if somebody has it, or I'll stay outside. So yeah. We do actually basically the key-based access. I have the document ID, which in our case the document ID is a partition ID. Therefore, we use that. We are not really using the document DB's document ID. We sort of really doing a simple query on our partition ID, which is, let's say in our case, user ID. Yeah. South Africa?
Yes. Mike? Yes. Cosmos DB is a Ring 0 service, and so therefore it's by default going to be available in all Azure regions, every single one of them. That's because South Africa hasn't launched itself for Azure just yet, but it is in the process of launching.
You can come to the mic so that people want to.
Oh yeah, can folks come up to the mic so that the folks in the room can hear the questions?
Sure. Are there any other direct query tools for Cosmos DB other than just the portal data explorer there that you showed?
Yes, although the experience is very similar. What we do is that data explorer that we embed into the portal is just an HTML/JS app that we have also embedded in a few Electron applications. Okay. So for example, if you download our Azure Storage Explorer, that is an Explorer tool local to the desktop that has both support for Azure Storage as well as Cosmos DB and a few other products. We've embedded the same experience there as well, if you want a local version.
Okay. Do you have any plans to have any other type of, any new ones by chance? Any other tools?
Yes. The spirit of why we approach the problem the way we do is that way we can have a unified experience everywhere. But we are looking at how to bundle that into something that's most convenient for you. Okay. If there are specific ways you'd like to see that shipped to you, or if there's certain experiences that you're looking for, actually, I would love to hear. And if we want, we can take a.
Yeah, sure. Okay,
chat on
cool.
this offline.
Yeah, when we've played around with it, it's a little clunky using that Data
Okay.
Explorer at times, I think.
Yeah, I'm happy to get your feedback on this.
Okay, cool. Great.
So now we are using Cosmos DB in our environment, and we see the performance issues with through the MongoDB. So so when I think it is actually evident with most of the developers that they are not seeing the optimal performance with responses when they use the Cosmos DB with Mongo.
So you're using MongoDB APIs on
Yeah,
Cosmos
right.
DB?
Yeah.
And then you're not seeing, what is you're seeing performance?
So the response times with accessing the data, and even though they increase the partitions and RUs, so when they increase the partitions, the response times get slow with MongoDB. So essentially, all we figured out is that the something with the SDK of MongoDB. So we are pursuing that, but some investigation is going on. But do you have any insights with that? That's
Well,
what something.
The man,
I think the main thing here is to look at the details. There's nothing inherent to MongoDB API, but rather it's going to be based off of the request, right? So if it's a write request versus a read request, if it's a query, are you using the index? Are you not using the index? I think the best way to troubleshoot this is you'll want to give us like a big dump in terms of what exactly the nature of these requests are. I think if you can you send us a support request for this? We'll be happy to look through all the details and troubleshoot it.
are you actually seeing variance in performance? Are you seeing performance latencies are high?
Latencies are high. That is
Okay.
the core issue with this. So here, the most of them are write request. So some of them always include read as well. So more or less, it is not just one person or one developer, but at least 3 to 4 teams have been experiencing that. Yeah, we are actually pursuing that actively with support request already. I'm just try to bringing up here. Okay, thank you.
Yeah, we'll take a look.
Yeah.
The choice of regions on which you replicate is actually completely controlled by the user. We won't automatically just put data, let's say in Australia or into a country, but instead it's completely toggled by that map. What you want to do is you want to have your administrators configure which regions you actually want your data to reside in.
Yeah. Because we have the same issue. So we have internally for the Microsoft stuff, especially we run in China, and then we can only run in Hong Kong, and then so or Singapore or certain things there are restrictions. So we need to manage it where the regions are, where we replicate it. See, this is an example where you may have to really partition your workload in that fashion, because this global, technically Cosmos DB can run anywhere. Practically, because of the constraints, I cannot. Therefore, I take the overall workload and then I say that I make it into 2 collections. One collection runs everywhere. One collection can run only in China for the China customers. I could have really created one global collection, but it really, compliance purposes, I cannot do that. So we do those kinds of things actually.
And I have seen people do this hybrid approach where they might have 2 sets of accounts. One is a global account for anything that is not sensitive that you can replicate everywhere, and then another account where they manually configure just a small set of regions, let's say just China or just Germany or just a specific set of regions. And what they do is they just partition the data across these 2, depending on how sensitive that data is.
Another question, maybe a little. So how the Azure Cosmos DB handles the parallelism? Is it defaulted, or do we need to configure
For the query or for the querier? Yeah, it automatically does it. Yeah, because if you physically Cosmos DB partitions your work across multiple partitions, when you run a query, it actually does that for you. You don't need to worry about that.
So it's basically default. There is no.
Yeah.
There are options if you want to manually configure. So there's two ways of looking at parallelism. One is parallelism of across your overall request volume. That, of course, you control. But then there's also the parallelism of an individual query. We, by default, have like it's like a fast start algorithm, kind of like the TCP fast start, where we grow the number of connections to increasingly parallelize the request. However, if you know ahead of time exactly how many partitions you want, and right off the bat you want to ask all of them, if you look within the query options, there's a parameter called max degree of parallelism. And rather than setting that to -1, which is automatic, you can set it to a constant value.
Yeah. Actually, my philosophy is, why are you doing that? I can sit with you too, because I want to optimize away. So I think, again, my philosophy is that if you want to run sophisticated queries, push it to the lake or push it to DW and then use, because you can, there are ways to play these things, right? So that, because it all depends on eventually how much throughput, how much your expectations are. If you can tolerate little lower latency, I mean like longer time, it's okay, but that depends on your workload. For us, everything needs to be single digit millisecond. We cannot tolerate anything, so more than that. So yeah.
So is this indexing like similar to RDBMS indexing? Because how does it handle the fragmentation or anything?
The implementation for the index is quite different from an RDBMS. What we do is we implement an inverted index on top of, we have our own data structure around this called the BW tree. We have actually a paper that we published for the VLDB conference on this.
Yeah,
we can,
like. Indexing is little interesting. So I can actually explain to you after the talk. That was the one, that slide that I wanted to talk, the under the hood. I think that actually requires a whole talk, so yeah. Go ahead.
Recommendation on small document size, what's small?
1K is the best, because then that's the best price, it's like, I want, if you can, but it's not always possible. So because it depends on your workload. Don't really be artificially try to squeeze that, right? But where possible, we actually reduce it. In fact, what we have seen in our cases, there are some workloads that actually have like a megabyte document. And it finds out that big chunk of it, we never even touch it. And putting everything in one place and then paying the cost of really is, so we broke it. It's like vertical partitioning. We created 2 separate collections.
basically the scope of when we do reads and writes is at the document level. So if you have, let's say, a 1 megabyte document, but you actually use, and you're wanting to read and also update that entire megabyte, it's actually perfectly fine to chunk it in that manner.
Yeah.
But if you find yourself that, hey, I have a 1 megabyte document because it's a large unbounded array, and for example, I just want to insert an array element, that's like a 1 KB change, well, you're going to pay the update cost of the entire 1 MB document just to do that array insert. In that case, maybe those array elements should be broken down into smaller documents so that you can do a 1 KB insert as opposed to a 1 MB replace.
Yeah, yeah, that's what we do. We do that, and then both of them share the same primary key. So it generally falls into the same partition, but those are 2 separate, document collections. That's how. Yeah, yeah. There's, by the way, these techniques help not just only Cosmos DB. In general, any database system, in the end, it's physics. Like, how much storage are you taking? How much CPU are you taking? How much IOPS are you taking? Any system is going to charge you. In fact, SQL has DTUs, which are very similar, and then you can optimize those also. Yeah, I don't think, right now the whole document gets replaced, right? Let's say I have a nested structure, I change one property, but still I need to write the whole document.
A lot of that is actually to achieve very, very low latency, high throughput writes. What we do is we do these blind writes, where when you do a replace operation, we just prep it somewhere and we do an atomic compare and set operation where we change the pointer to where that record's pointed. That way we don't have to do any read IO to do that update.
I think this is actually, it's like if you look at this is like going into deeper. Cosmos DB never does every in-place writes. SQL actually does in-place updates. And that causes, sort of there are costs, and then in terms of the overall IO throughput as well as the, the concurrency, because Cosmos DB never does anything in place, everything is like a version. Some of them are Delta versions. You never have to block. A typical scenario in B trees in SQL is like if you are monotonically increasing primary key, your updates actually, you're like the right-hand side of your B tree becomes hot, so because everybody is inserting, because the key is increasing incrementally. Cosmos DB doesn't have that problem because there is nobody blocks, because writes never block on each other.
So in principle, I mean, this isn't something we've wanted to do just because we do optimize for high concurrency, low latency workloads.
Yeah.
It is something that we are discussing internally on whether we want to support, because we are also looking at CRDTs for our active-active, our multi-master capability, in which case a patch API would be useful. But in the context of, if you're just looking at this from general updates, this is a behavior that we actually want to steer you away from, because it's costly to do these in-place updates.